This is Mrs. O'Neill for AP Chemistry, Chapter 14, Section 7, Catalyst. So you should have watched the intro lesson on catalysts. So my notes are this. What does a catalyst do? Well, they speed up a reaction, but remember, they are not consumed in the reaction. In other words, they don't play a part in the reaction. A real one that's been going on for years is this elephant toothpaste demo. You might have seen it when you were young or maybe in another science class. So the flow chart, as he always gives us, very nice. Exothermic reactions, products have less energy than those reactants. You know that already. But there's that transition state that we talked about before. It is that molecule that's kind of put together, again, in the right way in order to form those products. So he talked about enzymes. Again, a lot of biochemistry going on here. So how do they work? Again, here we have a large activation energy. To get us from H2O2, hydrogen peroxide, to water and oxygen takes a lot of energy. However, scientists are thinking, there's a number of atoms with those iron in the middle. Maybe we can do something with that. So what happens? We have that original reaction with a high activation energy. And now because of this catalyst that they add, it actually lowers the energy. Okay, it lowers that activation energy, which means it's a smaller hill, which means it's a faster reaction. Notice we have the same reactants and we have those same products. So that catalyst is part of that transition state, doing something to that molecule that's kind of coming together, but it's really not part of the overall reaction. So again, sometimes it works by creating those new intermediates. So these are going to be new steps in the reaction. So if you notice again, there's an example of a reaction mechanism using a catalyst and forming an intermediate, but the intermediate then is used up in a later reaction as a reactant, and that catalyst then becomes that product because it's really not part of that overall reaction. So again, an original reaction versus a two-step process with that catalyst, but notice that we have two hills, but both of them are smaller than that original big hill. So that other intro lesson on the catalyst classes, again, my notes are this. They are important in manufacturing, refining, life in general. So these catalysts are used in multiple things. So again, that nice little flow chart as he always does. So in that acid-base catalyst in gasoline, he talks about adding, taking away, protons, reactants. He talks about sulfuric acid. Just gives you this nice example. So how about surface catalysts? Sometimes catalysts are just used on the surface of a metal. Again, getting something to break something down quicker or form those products quicker. So again, he gave you that nice analogy. So hydrogen again and ethylene, again, talking about more of this example. So hydrogen are those white circles, and again, more successful creating that ethylene using that catalyst. So we also talked about the Haber process, very, very important process when we're taking hydrogen and nitrogen to making ammonia. And again, enzymes in our body, the human body, that's again, biochemistry, lots of enzymes, catalysis, catalyst enzymes are used. And then, of course, he talked about that sugar and what happens. Again, those are really, really good notes or interesting notes if you're thinking about the biochem. So on to your notes packet. Your objectives for this section is to learn how these catalysts increase the reaction rates. So pause the video and read this over. So you're reading from here first, right? A chemical reaction, and then reading this. And actually, we're going to talk about this again later on when we go over the bookwork. So pause the video, fill in the blanks, read as you write, and then play to hear my words. Again, most of this you already know. What does a catalyst do? Well, it's something that's added to a reaction and it speeds it up. Remember that it does not act as a reactant or a product because it is reactant first, product later, and then it is canceled out and not part of the overall reaction. It lowers that activation energy and allows those reactions to take a different path. So I am going to go back real quick to this guy. Hopefully you read this over, but remember that it needs still the same amount of how do I want to say this? It's the same hill. We didn't change the hill. So for those people who want to go over the hill, that's fine. It's going to take a lot more energy, but that hill still exists. The catalyst actually just makes a new pathway. It makes that tunnel to go through the hill. So for those that maybe don't have the energy in order to climb up the hill, but want to take an easier pathway, it will now go through that tunnel. So we want to remember that this catalyst, even though it lowers the energy to speed up that reaction, that amount of energy technically is still there. That hill is still there. It's just taking a new pathway. Okay. And again, we've already talked about this many times. So what does it look like as far as a reaction diagram? Again, our red line here is the original reactants yields products and has to get over that hill. But once we add a catalyst, now there's a new pathway and it lowers that activation energy. So again, this is just another example using numbers. So hopefully that makes sense. So catalyst and rate. So again, the catalyst will speed up that reaction, but still, again, only to a certain point, right? And then that rate increases until those active sites are filled. In other words, at some point, the rate is going to level off because the rate is independent of that concentration. So at the end of the day, you still only start with so much concentration. Even if you add a catalyst, it's only going to go as far as it can at a certain point. So there are two types of catalysts. Homogeneous, same phase, so the reactants are both going to be gases or they're both going to be liquids. Heterogeneous means that those reactants are in different phases. So you might have a liquid and a gas reactant. Well, I have a question for you then. Does that make sense, right? Homogeneous would be harder because they're both in the same phase, so it's going to be harder to separate the two, versus heterogeneous, it'll be easier to separate that salt per se, solid, or let's say a piece of metal, let's say, from water. And of course, there's those biological catalysts that are very important in biochem. So can you fill this in before you play the video and get the answers? When we increase, decrease concentration of reactants, what's going to happen to that rate constant? And then what's going to happen to the overall rate of reaction? Same thing with temperature and same thing with catalyst. Hopefully that makes sense. And that makes sense. Does that make sense? Hopefully that does too. How about that catalyst? Yes, it does change that rate constant and it increases the rate. So I want to remind you, we talked about temperature and catalyst will change the rate constant because of that Arrhenius equation that was brought to your attention earlier in the chapters. So stop the video again, read over this. Again, make any notes on the side. You have plenty of margins, or you can put this in your video notes notebook, anywhere that you see fit. But most of this we already went over. It's just reminders. So how about some AP multiple choice practice? Can you answer the following? Again, pause, see if you can answer. Hopefully you got that. If you did, you're good to go. You might want to still read the understanding of it or the explanation of why that's the answer. How about this guy? Pause, see if you can figure out what's going on here. Hopefully you got E. Again, if you got it, great, but you still want to read that explanation. How about this? Pause the video. Can you figure out the rate law expression? Hopefully you got C. Again, read that over and hopefully it makes sense. 10. Hopefully that makes sense. And see you in class.